In this video, we're going to deal with the interesting case of tube-typed instruments, where we actually can play notes by using the fact that there are boundary conditions on an open or partially open tube. Now, you may remember that we had stringed instruments in which you have a string attached to one place and some other boundary, whether that's by a weight or what have you, and only certain wavelengths of the string are allowed because of the boundary condition. In the same way, a tube, whether it's open or closed, provides certain boundary conditions which limits the wavelengths of the pressure waves that can be set up inside of that tube. Now, in order to make the calculations simpler in the same way they are for the string, we're going to have to make an assumption here. And the assumption that we're going to make is that the diameter of the tube is small in comparison with the length of the tube. If we do that, then what we know is where the pressure node is, or in put another way, the displacement antinode. And this will be at the location of an open end of a tubed instrument. If the instrument happens to be closed end, then exactly the opposite will be the case. At the closed end, you have antinodes. So, key thing, pressure nodes open end of tube. Pressure antinode closed end of tube. Now, an open tube is when both ends are open. You'll never have a case where both ends are closed. In that case, no sound gets out of the tube. But you either have both ends open or one end open of the tube. So let's look at the analysis for an open tube. So in the open tube, we have the situation like this. The tube is closed on no ends. So let me draw that right, like this. And I'm going to draw two pictures because I'm going to draw a picture for pressure and I'm going to draw a picture for displacement. So this will be the displacement picture, or what I generally prefer, the pressure picture. This tube's got a length here of L in both cases. And we are assuming that this gap, this diameter in the tube, is much smaller than that L. If that's the case, then we know the following. For the pressure case, the wave will have no displacement at these ends. And so the possible wavelengths is a wave that looks like that, or equally it could be like that. But it ends here. And that means that the wavelength here, since that's only half a wavelength, the wavelength of the fundamental frequency is 2L. This is exactly the same thing that we found for the string. Likewise, we know that the frequency is equal to the speed divided by the wavelength. So the fundamental frequency is V over 2L. And because we want to do other frequencies, we'll just put a 1 up there. We can also draw the picture of the displacement. So let me draw the displacement. It's going to be the opposite. It will have a max or min and have to go down like this. Or likewise, if it was a minimum displacement, it would go up to a maximum displacement. So again, half a wavelength. But here you have maximum or minimum displacement at the ends. And in the pressure case, you have no pressure change at the ends. They are nodes. Now, the nth harmonic and correspondingly n minus 1 overtone can be given by the following formula. F to the n is equal to n times the fundamental frequency, which is n times the speed of sound in the tube divided by 2L. This is exactly the same formula as for the string case. So if you know the strings, you've got the same thing. It's just we're dealing with pressure waves instead of string waves. Just the same formula as for strings, with V being the speed of sound. Now you may notice that an instrument will change its frequency slightly on a day-to-day basis, since we know that the speed of sound slightly changes. So consequently, people have to tune instruments. There's a couple ways you could do that. For instance, one way we could do that is to make this tube so that we could slightly change its length. And in fact, that's what happens in mouthpieces and various types of instruments in band. Now let's look at a closed tube system. In a closed tube system, we mean by that one tube is closed. And this happens to produce some very interesting changes to the problem. And its formulas are different than the past formulas we have looked at. So in this case, we have something like this, but now it's closed. So, closed on the ends. Still talking about the same length, L. Same length, L here. And this will be displacement. And this will be pressure. Now, what's changed? Well, what's changed is right here. In the case of displacement now, this is going to be a node. And the open string will still pay the same as it did before. It'll be an antinode, so this will go down like that. Or, of course, it could be a minimum displacement going up like this. So we see this as a node, and we see this point as an antinode. If we look at it from a pressure standpoint, then this point here was a node, and this point there is an antinode. So antinode and node. So either we pull a bunch of the particles away this way, there's no way for them to fill on this case, and we have a rarefaction that is a very low pressure, or we push molecules this away and there's no place for them to go, so they build up and the pressure gets high. Now in both cases, if you look at that, this length does not come back down. This is not half a wave, this is a fourth of the wave. So the wavelength here, wave 1, is only a fourth of the length. So since it's a fourth of the wavelength, it will take 4L in order to get this. And the fundamental frequency is V over 4L. So it's half the open tube. So longer wavelength, lower frequency. Even more interesting than that, not all overtones are allowed. Only odd harmonic frequencies can happen. So that's the first fundamental frequency. This is the fundamental. Let's look at the next one. The next possibility would occur when the following happens. Again, it has to be 0. It goes up, and it comes down, and it goes down to about there. Or it's here, it goes down, and goes to there. In either case, this is the next one, and it's going to be 4L over 3. So the next frequency that can occur is equal to 3 over 4L, or 3 times F1. This is known as the first overtone. And usually they just say. So overtones in this case only occur in odd multiples of the fundamental frequency. You can't have the second, because if you had the second, then what would have to happen here is that this thing would have to go up and come down, and this would have to be a node. But this cannot be a node because it's an open end. So in other words, what I'm saying is, if you had a pipe like this, F2 is not allowed, because it would require a node on both ends. And you can't have a node on an open-end pipe. So you can only have the odd ones.